Hey stats people, hope you guys are good, doing great today. So we know how to make confidence intervals for the mean. We know how to make confidence intervals for a proportion P. But one thing that we haven't talked about is perhaps a desire to make a confidence interval for a variance or a standard deviation, right? Standard deviation we know is sigma, variance we know is sigma squared. That's that relationship. Right? And if you think about it, that might make sense that we might want to make a confidence interval for variance or standard deviation. If I am a manufacturer and I am manufacturing, I'm making some part, some component, something, right? I know not every single time am I going to produce the product to the exact specifications that I want. There's going to be some variance to them, right? It's not always going to be perfect, okay? And what I don't want is I don't want there to be a lot of variance in my product. I want to keep it hopefully as narrow as I can. So what we want to learn today is how do we make a confidence interval for variance or standard deviation? That way, as a manufacturer, I might be able to say, I'm 95% confident, okay, that the standard deviation for the weight of this part is between, a 0.1 and 0.15 pounds, something like that, all right? So we want to try to control that variance and make confidence intervals for those. So just like with means and proportions, we have to have a point estimate. Okay. Now we know x bar is the point estimate for mu. We know p hat is the point estimate for p. What is our point estimate for our standard deviation and our variance? Well, our sample standard deviation is our point estimate for the population standard deviation. And s squared, the sample variance, is the point estimate for the population variance. So that's pretty simple. Okay. Now, to do these, we have to introduce a new type of distribution. We're used to our our standard normal distribution. We have also learned about students' t-distribution, okay, which is a family of curves that depends on the degrees of freedom. Well, the type of distribution, okay, that we use here is called a chi-squared distribution. Here's a Greek letter chi. Kind of looks like a big S, little curvy there on those. But this is the chi-squared distribution. And there's a lot that we need to learn about this to use it. It's not too complicated, but it's different. All right? So, number one, all values of the chi-squared distribution are greater than or equal to 0. What we end up doing is we take our standard normal distribution and we square those numbers. So recall that the mean on the standard normal curve is 0, okay, and then we've got 1, we've got 2, okay, we've got 3 out here, right? -1, -2, -3. Well, what happens as I square all the values on this? They all become positive, don't they? And in fact, if I square the standard normal curve, okay, I get the chi-squared distribution with 1 degree of freedom. Okay? And I have a graph that's going to show you some more here in a second. So one thing that we have to know is the values are always greater than or equal to 0. Okay? So let me get to that graph here because it's a family of curves, and that's the next thing I want to talk about, determined by the degrees of freedom. So here are the graphs of several of the chi-squared distribution curves depending on degrees of freedom. In the red, okay, that's 1 degree of freedom. Okay, like I said, that's like if we just squared the standard normal curve. Most of the data here is at 0, and 0 squared is 0. It ends up being the peak, and then it really comes down and approaches that x-axis as we move to the right. Now with 2 degrees of freedom, that's this kind of a brown tan color. And then we've got 3 degrees of freedom, Okay, this graph jumps to 5 degrees of freedom and 10 degrees of freedom. Okay, so notice that in all these curves, they're skewed to the right. Okay, and the larger the degrees of freedom, okay, the less skewed it is to the right. It becomes more symmetrical. Now, if I look at 5 degrees of freedom, it's not symmetrical, but it's more symmetrical than 3 degrees of freedom. 10 degrees of freedom is even more symmetrical yet. Okay? Now, I want to point out that this starts at 0. There are no negatives. So unlike our standard normal curve, which goes forever to the left, this doesn't. To the left, it stops at 0. But it does go to infinity as we go to the right. The total area under the curve is still 1. Okay? I talked about this already. It's positively skewed, so skewed to the right, and it's not symmetric, but the larger the degrees of freedom, the more symmetrical it gets. Okay? As the degrees of freedom increase, the chi-squared distribution approaches a normal distribution. If I said there were infinite degrees of freedom, it would look like our standard normal distribution. All right? So, as we make a confidence interval, okay, and I want to remind you, how do we do that in a standard normal curve? Okay. Do you recall if I wanted a 95% confidence interval with the standard normal curve, how did we do that? Well, we wanted to find a z-score on the right and a z-score on the left. Now, because of the symmetry here, we know that this is just the opposite of that one. And if we're finding a 95% z-score, we want the area between those z-scores to be 95% or 0.95. That's what we want here. Okay? And we did that, and we came up with a z-score of, well, for 95%, what is that? I believe that's the 1.96. And then this one would be negative 1.96. But we see that symmetry in the fact that they're opposites. Well, we're going to be making needing to find critical scores, critical values for our chi-squared distribution, but it's not symmetrical. So they're going to end up not being opposites. They're going to be different values. So let's find the left and right critical values for the chi-squared for a 95% confidence interval. Okay. So let me just draw a sketch here. Okay. And I said where n equals 10. So it's going to look a bit like this one. But I'm going to try to make it a little more skewed to try to prove my point here. Okay. So I should clarify. This is 10 degrees of freedom. If our n is 10, our degrees of freedom is 9. So it's not exactly that one that I just looked at. But it's going to look something like this, where it's going to come up, and then it's going to stretch out this way forever. Now what we want is we want to find a critical score here, which I'm going to call chi-squared left, and a critical score over here, which I'm going to call chi-squared right. And what we need is we need the area between those to be 0.95. Okay? Now, in the back of your book, in the appendix, after our t distribution, there is a chi-square distribution. Okay? So take a look at that table here. Okay. Now, in this table, it gives the degrees of freedom on the left because it's a family of curves like the t distribution. And then it gives us confidence intervals on the right. Well, not really confidence intervals. I said that wrong. Areas to the right. Okay. If you look at the diagram on the top, okay, and so there's two diagrams, and I want you to look at the one on the left that says right tail. This table only gives the critical value for the chi-squared to the right. Okay. And I know, like in our standard normal curve, it always gives to the left. So we've got to remember that in the chi-squared, it always gives it to the right. So what we need to do is we need to figure out Okay, what value to the right we need to look up to find these two different critical scores? If there's 0.95 in here, how much is there and how much is there? Okay, well, there's 5% left, and we take 5% and divide it by 2, we get 2.5%, 0.025. So for our chi-squared on the right, okay, 0.025 is to the right of that. So I am going to look up, okay, I'm first going to go down in my chart to 9 degrees of freedom. Then I'm going to go over until I'm to the 0.025 across the top. 0.025 corresponds to the fact that with a 95% confidence interval, with 9 degrees of freedom, 2.5% of the area is to the right of the chi-squared right critical value. So I find 0.025 on the top, 9 degrees of freedom, and I see 19.023. 19.023. Okay, hopefully you see that same number. Now, how do we find the chi-squared to the left chi-squared critical value? Well, the table only works to the right. What's the total area under the curve to the right of the left chi-squared critical value? Well, that would be this 95% plus this 2.5%. Or if you want to think about taking 1 minus the 2.5%, there is 0.975 is the area to the right of the left critical chi-squared value. So we need to look up, again, 9 degrees of freedom, but now across the top our area is going to be the 0.975 number. And as I scoot down, I get 2.700. Okay, so hopefully as you take a look at that, you get those same numbers. So this is what you need to do for every problem, because it depends on the degrees of freedom and the confidence interval. If there was, if n was 11, I would have different critical values. I would have to look those up. All right? Okay. So how do we find our confidence interval? Now that we know how to get our critical values, this is the equation that we're going to need to know. Okay. Looks complicated. Not too bad though. So if I'm going to make a confidence interval for the variance, sigma squared, it's n minus 1, sample size minus 1, times the sample variance times s squared, divided by the critical right chi-squared value. And then the other side of the inequality, again, n minus 1 times s squared over the left critical chi-squared value, which is kind of interesting. So you got to remember this, that on the left side of your inequality, you use the right critical value. And on the right side of your inequality, you use the left critical chi-squared value. Now, what if I want to do a confidence interval for sigma, the population standard deviation? Well, what's the relationship between the variance and the standard deviation? Well, we just take the square root, right? If I have the variance and I want the standard deviation, I take the square root. So what I'm going to do is I'm going to take the square root of everything here. It's the square root of n minus 1 times s squared over the chi right squared is less than the standard deviation of the population, which is less than the square root of n minus 1 s squared and the left critical chi-squared critical value. Okay, so if we're going to do this confidence interval, criteria, we have to make sure the population is normally distributed. We have to determine the degrees of freedom. Okay. We have to find our point estimate, okay, so s or s squared. We need to find the critical values. We just walked through that process in the last example. And then we find our left and right endpoints of our confidence interval using this equation. So let's look at one together. You randomly select and weigh 30 samples of an allergy medicine. The sample standard deviation is 1.2 milligrams. So notice right away, n equals 30, and this is the sample standard deviation. This is S, which is 1.2. Assuming the weights are normally distributed, okay, so criteria, normally distributed, we've got it. Construct the 99% confidence interval for the population variance and standard deviation. All right. So we have it normally distributed. What's our degrees of freedom? Okay. If n equals 30, our degrees of freedom is n minus 1, which is 29. Remember, if it's not in the table, round down, right? So if n was 40, degrees of freedom would be 39. 39 is not in the table. I'd have to round down to 30. So remember to always round down. All right. So we've got this. We've got this. We have our point estimate S. Okay. Find the critical values. That's what we did in this problem. So I'm going to draw a sketch of a chi-squared distribution. Okay, something like that. I'm going to set up my right and my left chi-squared critical values. I need a 99% confidence interval, so I need the area between these to be 0.99. So what does that leave on the outsides? Well, it leaves 1% left. So this would have to be 0.5%, 0.005. And same with this, 0.005. So now let's look up in our table the right critical chi-squared value. So I'm going to go to 29 degrees of freedom. The area to the right of it is 0.005. So on my table, that's all the way to the right, 52.336. Our left, 29 degrees of freedom. What area is to the right? 0.995 is to the right of the left critical chi-squared value. So 29 degrees of freedom, 0.995, that's the first one, 13.121. All right, got that. Now it's time to find the left and right endpoints of our confidence interval. So this is where we use our formulas. And on this one, I asked for confidence intervals for both the population variance and the standard deviation. So here we go. N minus 1, 30 minus 1, right? That's just the degrees of freedom. That's 29 times S squared, 1.2 squared. I didn't rewrite this formula, but I'm using this one right here. N minus 1 times S squared over the right critical chi-squared value right here. 52.336 is less than the population variance, which is less than, and this is 30 minus 1 times 1.2 squared over our left critical chi-squared value, 13.121. So now I need to grab my calculator, which I don't have out, so I'm going to pause my video and be right back. All right, I grabbed my calculator now, and while the video was paused, I typed in both sides. Okay, so hopefully you're typing it in too to make sure that you see the same thing. And for my left endpoint, I end up with 0.798. And for my right, I ended up with 3.123. By the way, notice that the right critical chi-squared value is always bigger than the left. So we put the bigger number on the left, it's going to make this side smaller. And if we put the smaller number in the denominator on the right side, it makes that number bigger. Okay, but this is our 99% confidence interval for the population variance. I'm not going to write out the sentence here because I don't have enough space. But I would say that we are 99% confident that the true population variance of the weights of the allergy medicine are between 0.798 milligrams and 3.183 milligrams. Now, how do I get the standard deviation confidence interval? Well, we just take the square root. Okay? So I'm going to take the square root of 0.798, and I have 0.893, and I'm going to take the square root of 3.183, and I get 1.784. So I am 99% confident that the true population standard deviation of the weights of these allergy medicines is between 0.893 milligrams and 1.784 milligrams. So we know where we think that the population variance and standard deviation was in. So if I'm the manufacturer, I can say, yep, I feel good about the variance or standard deviation of my product. If these numbers were bigger, I might say, whoa, there's way too much variance. We need to fine-tune what we're doing so we are more consistent as we manufacture our whatever it is, in this case, allergy medicines. All right? So that's an introduction to the chi-squared distribution and how we do confidence intervals for variance and standard deviation. Thank you so much for watching, and we'll see you later.